So my colleagues, Anthea Koster, Shenrong Zhang, and Larissa Goncharenko at Haystack are involved in this, but I want to emphasize this is a natural experiment, and it takes a global village to do this, and we're going to use as much global data as we can, so honestly, I couldn't fit all the collaborators on there. Again, our goal is to observe changes in the upper atmosphere. You've heard about the ionosphere in the American longitude sector, and I'll tell you why, not just over North America, that are triggered by the eclipse using radars, even satellites that are passing by, and GPS. We've mentioned what the ionosphere are. This is really the charged part of Earth's upper atmosphere. Every day it's created in the sunlit part of the planet by extreme ultraviolet photons coming from the sun. From the neutral atmosphere, we make electrons and ions. It's got a complicated structure. This is a movie of 24 hours of the ionosphere. It's naturally complex. Red is more electrons, blue is less. It varies in space and time. This is something called space weather. We would like to understand more about these variations by using the eclipse as a natural, large, active experiment. This is a radar that I help run in Massachusetts. The vertical axis is altitude. Space station's about in the middle. That's 24 hours of the life of the ionosphere. Even in altitude, it's quite complex. This is another version of space weather. We're hoping to use the eclipse to understand that. This is our colleagues at NRL that Greg Earl mentioned. This is a modeled effects during one of the eclipse passages on the number of electrons in the upper atmosphere. Notice that both the northern and the southern hemispheres are affected because they're electrically coupled. Eclipses launch ionospheric waves. Nature doesn't like having more in one place and less in another one, and it tends to try to propagate waves out from the spot. These are called traveling ionospheric disturbances. We need a whole global view to see these and watch these waves travel. They not only travel horizontally, this is a picture of them traveling vertically over several hours. These, again, are traveling disturbances that are the basis of space weather, and we're trying to use the eclipse to understand these better. You could watch this movie all day long. This is the global network of GPS observations. They're being used for earthquake research. You can process them to get a global view of the ionosphere and spend your entire career looking at waves in this. The eclipse is going to make a big splash in the middle of that. It's obviously not the first time that people have looked at the eclipse from the ionosphere. This is an eclipse in 1940 from NRL, but the observations were few and limited. So we learned some things, but we didn't have the global view that we have now with current technology. So we're going to be using, Greg was talking about large radars. Those are large. That's 1,000 feet in diameter. In addition, there's a satellite passing by, NASA timed, which tells us something about the neutral atmosphere, the source of the ionosphere. And we're going to take all these GPS receivers, process them, get not only the hole that is going to appear, but watch the waves propagate. And I can guarantee you we'll find some phenomena that I don't know about that will have us all scratching our heads as a global community. And those have been known for a long time. That's how the ionosphere gets produced. It's really natural chemistry. Henry Rishbeth, a very famous British physicist, said this is a unique opportunity for studying both what's coming in from the sun and how the ionosphere reacts. We have a lot of tools. I've mentioned GNSS, that really is GPS plus the other 3 satellite networks. I can pull the ionosphere out of that. We're going to be doing that. I mentioned these large ground-based ionospheric radars, and then we very happily have the time satellite passing by. These very large radars actually scatter a very, very weak signal off the natural electrons in the upper atmosphere. By processing that right, we can measure the weather. We can measure the density, the temperature, the velocity, the composition. That's the charged part. The NASA timed satellite has a camera at ultraviolet wavelengths that I can tell you what the neutral part of the atmosphere is, the source of the ionosphere. So again, I'm looking for the big picture. I'm going to combine all of this and work with my colleagues who are making these other measurements. And this is the large picture that puts some of their more focused observations and those from our radars in context. And by looking at things in multiple scales with multiple different eyes, we always learn more than we do in looking at every one individually. So this is the big picture. We happen to have these 2 satellite passes in the blue passing right by the United States, measuring the neutral atmosphere at the same time that that track is going through, punching interesting waves in the ionosphere that affect the whole US. We're going to be transmitting what we measure from one of the radars, Millstone Hill in eastern Massachusetts, live. There's the URL. You can go to there on the day of the eclipse. We're going to be running 5 days centered on the eclipse. You'll get to watch the whole appear live. So we're really hoping that by putting all of this unprecedented multi-scale level of information together, we can both advance the science of just understanding how the atmosphere behaves and discover new things that we did not see before. And so we're really excited about this, and we need to work in the community, and that's what we're going to do. So I really appreciate the opportunity. Thanks.
Thanks, Phil.